These are problems from covering Newton's laws, and it's going to be almost exclusively Newton's second law, simply because the first law doesn't include any calculations. It just states that the law of inertia, and the third law is simply the action and reaction principle, which pretty much says that the equal and opposite force, well, is equal and opposite to the action force. So in any case, most of these problems are Newton's second law. The sum of the forces, or the net force, equals mass times acceleration. Okay, let's get started. The first problem is chapter 4, number 2. And it says, what is the acceleration of a 40 kilogram block of cement when pulled sideways with a net force of 200 newtons? So we have m equals 40 kilograms, and we have a force here of 200 newtons. And so this Greek woman is pulling it to the side. And by the way, it would be getting faster and faster and faster. So not just at a constant velocity, just that, yeah, it's just getting faster. So the equation is straightforward. F equals m times a, or sum of the forces, or the net force. And apparently we only have one force here. 200 newtons equals 40 kilograms times acceleration. So obviously, therefore, acceleration equals 200 newtons divided by 40 kilograms. That comes out to obviously 5. And on the side we can say, well, newtons per kilograms, that's the same. So I'm going to write here units. Well, the newton is obviously kilogram itself times acceleration, meters per second squared. And now we divide that newton by kilograms. So when we do that, we come up with meters per second squared, just as we should. So that means that the block is getting faster and faster relatively quickly, and at 40 kilograms, 90 pounds, it's kind of questionable that anybody could do that for a long time. So maybe just for a split second. It doesn't say for how long in the problem, but it just says what's the acceleration of a 40 kilogram block. Okay, this is chapter 4, problem 3. And it says, what is the acceleration of a 20 kilogram pail of cement when that is pulled upward, not sideways, with a force of 300 newtons? So we have 20 kilograms in here. I know it looks like water and the problem says cement. Oh well. And there is a force of 300 newtons pulling upward. So this Greek man is pulling it upward here, and it's getting faster and faster as he's pulling it upward. Okay, so we're going to write down force equals mass times acceleration, or net force equals mass times acceleration, or sum of the forces equal to mass times acceleration. Well, we have a force upward at 300 newtons, and that equals 20 kilograms times the acceleration. However, they say in here, what is the acceleration of a 20 kilogram pail of cement that is pulled upward, not sideways, exclamation point, with a force of 300 newtons. So the upward force is 300 newtons that the person applies, but there's also a downward force, which is the weight of the pail itself, and that is at 20 kilograms multiplied by 10 meters per second squared, 200 newtons. because they're in opposite directions, they would have to be subtracted, or I should put a negative in front of that. So therefore, negative 200 newtons down plus 300 newtons up. That of course comes out to 100 newtons equals 20 kilograms times acceleration. And of course 100 divided by 20 is 5. And as you noticed in the last problem, newtons divided by kilograms is the same as meters per second squared. So again, that pail of cement here is getting faster and faster relatively quickly as it's being pulled up. So that can only be done for a very short time. Okay, next problem is chapter 4, number 5, and it says, how much acceleration does a 747 jumbo jet of mass 30,000 kilograms experience in takeoff when the thrust for each of 4 engines is 30,000 newtons? Well, I multiply 4 times 30,000 newtons, that's 120,000 newtons, and divide that by 30,000 kilograms, so I come up with an acceleration of 4 meters per second squared. And the reason I didn't write that down is because look at some of the data here. They give a thrust of 26,000 kilograms. I don't know why they list this in kilograms. I should list it either in newtons or pounds. But that thrust here, when you multiply it by 10 meters per second squared, comes out to, well, 260,000. I'm going to round this here maybe to 250,000 newtons per engine. And then the problem they told us that each of the engines has 30,000 newtons. I also looked up the mass of a jumbo jet, and it's not 30,000 kilograms, it's actually 300,000 kilograms. Oh no, 400,000 kilograms. Hold on. $400,000 So for my calculation, I like to use that new number, those new numbers. So for force equals mass times acceleration, we would have 4 engines times 250,000 newtons equals 400,000 kilograms times acceleration, and therefore we come up with an acceleration of 1 million newtons divided by 400,000. So 1 million divided by 400,000, 2.5. I could have done this quicker and just say 10 divided by 4 or 1,000 by 400, but in any case 2.5 meters per second squared is the acceleration. Chapter 4, problem 7. A firefighter of mass 80 kilograms slides down a vertical pole with an acceleration of 4 meters per second squared. What is the friction force that acts on the firefighter? So what we would have here is the mass of the firefighter is 80 kilograms. What we also know is that he accelerates down at 4 meters per second squared, which means he's not in free fall. If he was in free fall, according to his weight of FW, his weight of 800 newtons, right? 80 kilograms times 10 meters per second squared, then he would be accelerating downwards at 10 meters per second squared. But he's not, because there is of course friction on the pole. So this one up, and which we're supposed to figure out. And the way to do that is to say, okay, we have a number of forces that equals mass times acceleration. And one of the forces we don't know, the frictional force. Another force we do know, and because it's going down, I call it 800 newtons downward, minus 800. And that equals 80 kilograms. And that times, need a little bit more space, 4 meters per second squared. But just like the force, his weight being downward, his acceleration is also downward, so I should call this a negative here. Okay, let's see what we get. The frictional force minus 800 newtons equals negative 320 kilograms meters per second squared, which is also newtons. And now we add 800 newtons to the other side, and we come up with a positive 480 newtons. You can do that on a calculator. Negative 320 plus 800 is 480 newtons. So that's the force up. That also makes sense. It's quite a bit smaller than 800, so we probably do come up with an acceleration of 4, and we can check that. 800 minus 480 is 320. That force is still downward. Divide 320 newtons by his mass is the given 4 meters per second squared. So what I just did in mid-air here was a check of our answer. Chapter 4, Problem 9. Sprinting near the end of a race, a runner with a mass of 60 kilograms. It's about 130 pounds. Accelerates from a speed of 6 meters per second to a speed of 7 meters per second. So he is first here at 6 meters per second, and then he has accelerated to 7 meters per second. A, what is the runner's average acceleration during this time? Oh yeah, and it says in 2 seconds. In 2t equals 2 seconds. So they're asking in part A, what is the acceleration? Well, from a previous chapter we know that the acceleration is change in velocity over the time interval. So a change in velocity would be 7 meters per second minus 6 meters per second divided by the time interval of 2 seconds. 7 minus 6 is 1, divided by 2 is 0.5. And the units are meters per second, so meters per second squared. Okay, second part of the problem says, to gain speed, the runner produces a backward force on the ground so that the ground pushes the runner forward, providing the force necessary for acceleration. Calculate this average force. I need a little bit of space here, so I'm going to see if I can move the stuff out of the way. Okay, so there is a force backwards that the runner exerts on the ground. And therefore there is a reaction force that the runner experiences of equal magnitude but in the opposite direction. So the runner pushes on the ground backwards, and the ground in turn pushes on the runner forward, equal and opposite force. The two are equal to each other, and now the question is how much of a force? Well, the runner accelerates at 0.5 meters per second squared. The runner has a mass of 60 kilograms. We're supposed to figure out the force, so we're back to Newton's second law. Force equals mass times acceleration. And so we have force equals 60 kilograms times 0.5 meters per second squared, and therefore the force is 60 times 0.5 is 30 kilograms meters per second squared is newtons. Notice that the weight of the runner is not figuring into this formula because we're talking about the forces, or the force in the horizontal direction, and the weight is in the vertical direction, a weight of 600 newtons, which by the way is cancelled by the support force on the ground on him, also of 600 newtons up. But those two forces are in the vertical, while here we're talking about the force in the horizontal that accelerates them along the horizontal. Chapter 4, Problem 10. Before going into orbit, an astronaut has a mass of 55 kilograms. While in orbit, a measurement determines that a force of 100 newtons causes her to move with an acceleration of 1.90 meters per second squared. To regain her original weight, should she go on a diet or start eating more candy? Because it's a she, I figured I'd get a picture of a female astronaut. I looked up her name too. So her mass is originally 55 kilograms. Now she is on board the space station or the space shuttle, and while in orbit, a measurement determines as a force of 100 newtons causes an acceleration of 1.90 meters per second squared. So mass times that acceleration, force equals mass times acceleration. So it's going to be 100 divided by 1.90. Come up with 52.6 kilograms. So 52.6 kilograms. So that means while in orbit, she has lost 2.4 kilograms due to the typical body mass loss that astronauts experience when they're outside of gravity, because their bones don't have to support their body anymore, and so while they're still eating, they're still easy for them to lose some of their mass. So they're on an interesting diet. So it's important for them to actually keep track of their mass. Now the thing is, in orbit, how do they actually measure their mass? Back on Earth would be easy, just stand on a scale, but a scale is not going to work in orbit. So this one is being used, a body measurement device where they strap themselves in, and then this one is set in motion. It vibrates forth and back, and by how much it vibrates forth and back, that tells the device what kind of mass is being strapped in, and that's how they determine their mass. So this is chapter 5, and I'm starting out with what's called a one-step calculation, number 1, so I call this OSC. And even though the chapter name is Newton's third law, as I had mentioned before, for Newton's first law, Newton's third law, there's really nothing to calculate on the law of inertia. There isn't. On the action-reaction principle, it's pretty much if there is a 40 Newton force on one object acted on by another object, then, well, there's a 40 Newton force on the other object, just in the opposite direction, so there isn't really much to calculate. So even in this chapter, they're doing some Newton 2 problems.
Okay, so let's look at the first one. It says calculate the resultant of the pair of velocities 100 kilometers north and 75 kilometers south. Calculate the resultant if both of the velocities are directed north. And I'm going to start with by the way, I don't need the calculator here. I'm going to start with the second part, which says that both of them are north. So this one here is pointed 100 kilometers per hour north, and this one is pointed 75 kilometers per hour north, and then I just add the two, and it looks like this. And I think we already know that we come up with 175, but this is the way on how to do it properly. And so that's how to add them, and it's pretty much, in order to add them by vectors, go from the tail of the first vector to the tip of the last vector. So from here to here, align them tip to tail, and then go from the tail of the first vector to the tip of the last vector. And obviously I do come up with, when I add these here, come up with 175 kilometers per hour for the second part. Okay, the first part says, I'm going to grab these two here and copy them. There we go. But this one now points in the opposite direction. And again, they're added in the same way. Put them tip to tail. And maybe I shift them just a little bit here so to align them nicely with the squares, hopefully. Yeah, I think that looks a little better. There we go. So tip to tail, just like I did over here. And now the resultant is going from the tail of the first to the tip of the last. And when you look at it, 100 kilometers per hour north, 75 kilometers per hour south, you would have to subtract them. You come up with 25, and that's what the arrow is showing here as well, 25 kilometers an hour. The next problem says, calculate the magnitude of the resultant of a pair of 100 kilometers per hour velocity vectors that are at right angles to each other. So each one of them is 100 kilometers, and in order to add these properly, I know in the book he uses the parallelogram rule. I like to do it this way: tip to tail, the two vectors, and then I go from the tip of the first to the from the tail of the first to the tip of the last vector. I hope I had mentioned it in the previous problem as well. And that's what I come up with. And now I can measure that. And let's see. So this here would be 100. I know it's not totally parallel, but close enough. That's a little better. I don't think I get it any better. I don't get any better than that. So it's 100 right here, and now I'm trying to find that spot right there. I believe it was here. So 140. By doing this graphically, 140 kilometers per hour. And if I do it by algebra, by the way, I forgot to write down here that this is chapter 5, one-step calculation number 2. Okay, so if I do this according to the algebra, they're saying that if they are at right angles to each other, then the resultant vector r equals x squared plus y squared. Take the square root, so it's going to be 100 kilometers per hour squared plus 100 kilometers per hour squared, and then take the square root of that. And when I do that on the calculator, I come up with the square root of 100 squared plus 100 squared, parentheses, enter. 141, well, that's what I measured as well, 140. There's a quick way, but it only works if it's a right angle and if the two vectors are of equal length. And that quick way is that I take 100 and I multiply it with the square root of 2. But as I said, that only works if the two vectors are of equal length and are at right angles to each other. Chapter 5, one step calculation number 3, says calculate the resultant of a horizontal vector with a magnitude of 4 units and a vertical vector with a magnitude of 3 units, which means that what I just said about the quick way, that's not going to apply here because they're of different lengths. Okay, so here I have 4 units, here I have 3 units, and I put them tip to tail. There we go. And the resultant vector is this one. And now I figure what it is. And write that the resultant is the square root of 3 squared plus 4 squared. I always like to write the square root last so I know how big I have to write it. You can do that on the calculator. You can do it also in your head, because you're going to get 9 plus 16 square root of 25. 5. And by the way, if I tried this by measuring, I come up here with 3 units on this vector. In the vertical, I do have 4 units. Of course, that's what the squares are telling me. And then here, I indeed come up with 5 units. Chapter 5, problem, or OSC, one-step calculation number 4. And it says, calculate the resultant velocity of an airplane that normally flies at 200 kilometers per hour if it encounters a 50 kilometer per hour wind from the side at a right angle to the airplane. So this one here is the 200 kilometers per hour, and that's my scale. And then this one here is the 100 kilometer per hour crosswind. And when I put them tip to tail, again, so each 50, I mean that's the 50 kilometers per hour crosswind. So each square would be 50, and then the resultant would be tail of the first one to tip of the second one. And I'm going to use this one here and rotate it. And let's see, slightly more than 200. Well, when I do it with the Pythagorean theorem, I'm going to come up with that the total velocity of the airplane is going to be 200 kilometers per hour squared. I'll leave out the units here because I don't have enough space. 50 kilometers per hour squared. Take the square root. When I do that on the calculator, it's going to be square root of 200 squared plus 50 squared. And I come up with 206, and that's exactly what I had measured. 206 kilometers per hour. The next problem is chapter 5, problem 2. It says, if you stand next to a wall on a frictionless skateboard and push the wall with a force of 40 newtons, how hard does the wall push on you? And if your mass is 80 kilograms, what is your acceleration? So you're pushing onto the wall at 40 newtons. Well, the wall is pushing back on you. I put this in a different color in the opposite direction with the same force of 40 newtons. That's of course Newton's third law, equal and opposite forces, and that's what I had mentioned a couple of times before. There's really no calculation involved, which is why you see mostly Newton's second law calculations. So here's that. It says that, does it say a boy in here? If you stand, okay, so you would have to have a mass of 80 kilograms, 176 pounds. That would be nice for me. So probably not this boy here. Any case, you would use Newton's second law, force equals mass times acceleration, or acceleration equals force over mass. 40 newtons divided by 80 kilograms equals 0.5 meters per second squared. And that's how fast you or the boy would accelerate, as long as you are exerting that 40 newtons on the wall, and the wall in turn exerts 40 newtons on you, which might be just for a second or so. So for that time you have that acceleration, and it gets you some speed, and once you're off the wall, well, you're not accelerating anymore because you're not pushing anymore. Okay, chapter 5, problem 4. Forces of 3.0 newtons and 4.0 newtons act at right angles on a block of mass of 2.0 kilograms. How much acceleration occurs? So here we have this force acting that way and that force acting this way. In order to calculate, we have to put them tip to tail. And then of course my scale was, this here would be 3 newtons and this is 4 newtons, and the resultant would be this one here. We actually had that earlier. So 3.0 newtons, 4.0 newtons, and the result comes out to 5.0 newtons because we did that earlier. 3 squared plus 4 squared is 25. Take the square root, that's 5. However, they didn't ask for force, they asked for acceleration, but I calculated that for a reason, because in order to determine the acceleration I need the force anyway divided by the mass, which I almost forgot is given in the problem. That was 2.0 kilograms. So the force of 5.0 newtons divided by 2.0 kilograms comes out to 2.5 Newton per kilogram, or meters per second squared. Again, here on the side, when I come up with Newton kilograms, that's the same of saying kilograms meters per second squared. That's the Newton, and this would be Newton's second law. Force equals mass times acceleration. And now I divide that by actually the mass, the kilograms, and that's why these two divide, and Newton over kilogram is the same as meters per second squared. But I had mentioned that in the previous problem.